Hello everyone, welcome to FTC 731's introductory video on autonomous programming. Here at Team Wannabe Strange, we want to encourage and help incoming rookies navigate the world of FTC robotics across all of its departments, from mechanical to programming. Right now, you are watching the first part of a series of 2 videos on introducing autonomous programming to future rookie programmers. In this video, we will dive into how the autonomous op mode works, how to properly install the necessary resources, and what kinds of skills our team relied on in order to create a functioning auto. So welcome to 731's Intro to Programming Strange. Now, before we discuss anything else, I want to briefly touch up on how the autonomous op mode works in all FTC competitions. It is essentially a 30-second introductory round in the competition where all players are only allowed to let the robot run on its own, so no manual controls, just pre-programmed functions and live calculations that the robot performs solely on its own. What is pedropathing? Well, among other autonomous resources, our team frequently relies on pedropathing for its easy to use, yet effective structure for creating a custom auto. Not only does it pack live, continuous, and accurate path corrections, it is also relatively simple to tune, and most importantly, comes with an official visualizer tool, which is especially useful to see how you want to craft the predetermined paths of your robot during the first 30 seconds of a match. Now, of course, there are other resources for creating an auto, which is most notably Roadrunner. Especially during the past few years, Roadrunner was the usual go-to for crafting an auto. However, ever since the development of pedropathing, we saw that Roadrunner had generally fallen out of touch. Why? Well, first off, it relies on pre-calculated motor powers. Essentially, that means you need to manually tune and find out what motor power you need to set the robot at for each trajectory. Pretty tedious. Furthermore, it also requires complicated tuning for a whole lot of things beforehand. However, for pedropathing, you primarily need to only tune 4 main parameters, even or so. Your robot speed, mass, motors, and odometry pods, or otherwise known as encoders. Not only that, it also lacks an official visualizer, so you generally need to use some other third-party software, or at least a whole heck of a lot of time to think about how the robot should move during the 30-second auto period. And finally, it does not support Bezier curves. That is to say, it does not support curves at all, just straight linear lines. In case you don't know what Bezier curves are, they are essentially just curves with control points that stretches a part of the line toward the control point, thus curving said line. Bezier curves are especially useful because there may exist obstacles, and often there will, that may need to be quickly avoided, and provides the shortest possible path to intake or collect artifacts, that is, and score without bumping into any other artifacts or walls. So, how exactly do you set up pedropathing? Well, first you need to go to pedropathing's official website, which is, simply put, pedropathing.com. So we are here on the official website. Now there are quite a few buttons here, but the most important ones you need to focus on is just pedropathing here. So click on this button, and now click on Get Started. And now all you need to do is click on the installation section, which is right under Introduction. And so you can follow these instructions. The easiest one, I'd say, is to just copy and paste this link into just cloning a repository in Android Studio, or if that doesn't work, you can always try the manual method, which is a bit more complex, but it's relatively simple to do. From there, all you need to do is set up the tuning constants I have mentioned before. Now that you have set up pedropathing, how exactly can you use it? Well, as I've mentioned a while back, pedropathing actually supports an official visualizer. Now, in this visualizer, you can do actually a whole bunch of things. For one thing, you can add paths. Just click the Add Path button, and boom. And you can also move this little dot to change where your path goes. Most importantly, there's also position, so you should set your starting position. This is a legal starting point. And you can also change what setting the path is. For example, there's constant, linear, tangential. Most of the times you would use either linear and tangential. Constant is pretty useless because it just keeps the robot fixed at a specific angle you set throughout the entire length of the path. Linear, you can set specific degrees. For example, this is just automatically set at 90 degrees, and as it moves upward, it switches to 180 degrees. This can be very useful. But tangential, basically what it means, it just follows the trajectory of the curve, which is extraordinarily useful. Now, I mentioned a while back, again, that pedropathing supports Bezier curves. Well, here are the actual control points. As I mentioned before, it's like stretching a rubber band. It stretches your line and thus curves it around. So, most often than not, it'd be very much convenient, instead of having two separate paths, we have one path and we have a control point. And so if you press this play button, we can simulate it. And as you can see, the robot successfully intakes the artifacts. Now let's say you want to have it more complex. Well, let's say after the intake you want the robot to score. So you usually just make it a linear path, maybe not tangential. You'd want to set it as, let's say 0 degrees, and let's say this is about 45 degrees. And boom, your robot is ready to score. It's in the scoring position. Now, there's a bunch of options you can also do with this website, which is setting up your robot dimensions. I think our robot is 18 by 18. And you can also set up the motion parameters, which of course you need to figure out by tuning your actual robot. Here you can input the velocity along the X, along the Y, and also your acceleration. Acceleration is very important. You can also change your preferences, so you can add dark mode and a whole bunch of things. Now, once you have these curves, how exactly do I use it? I mean, it's a visualizer, but what can I do with it? Well, you click this button right here, and there's a thing called Java code. And it gives you the code for all these paths. And you can just copy paste it right into Android Studio. And that's how you can use these actual curves. Now that we have discussed the basics of how to use the visualizer, and of course how to export those paths you have created into your pedropathing project, it is about time we talk about state machines. Now, state machines are very useful, as they can allow the robot to transition between custom states you have made with an orderly manner. Essentially, it is just a structure for a set of states, instructions, and, of course, transitions. And most oftentimes than not, the structure pretty much boils down to step 1, step 2, step 3, and so forth. However, just know that each step requires its own set of steps as well, since it can get pretty complicated depending on what you want your robot to do. Nonetheless, it is extraordinarily useful, not just in the auto, but also in the teleop, as it can also be used for general robot mechanisms attached to gamepad controller buttons, like your right bumper being able to change the state of a robot arm from a resting state, a halfway rising state, and then to a fully rising state. I also like to think of state machines as like shifting gears in a car. That lever you pull down when you're driving is essentially a teleop for a car. You can shift the lever down one level at a time to shift the car between 4 states. That is, between park, reverse, neutral, and drive. And if you're in older vehicles, you might see a 2 and 3 state as well. Specifically, here's how a state machine would look like for a auto op mode. In this nutshell of a diagram, our programming department typically tackles state machines as what exactly would a robot do for this specific curve or trajectory it is going in. So, for example, in step 1, we have the robot move in a preload trajectory. In this step, we have it perform a series of 2 tasks. That is, we set the robot to its scoring state, which means turning on its flywheel and closing its gate to not let the artifacts escape. And then we have the robot move forward towards its scoring position to shoot the artifacts into the goal. In step 2, we first set the robot in the intake state, which means opening its gate to allow artifacts inside, and turning on the robot's intake system in order to push the artifacts inside the robot. The robot then moves into its intake position in order to intake the actual artifacts, and then we activate step 3, which makes the robot move towards its scoring position, switches to the scoring state, and then has it switch back into the intake state after it has finished scoring the artifacts into the goal. And of course, each path is different from the other, so we may have many more steps than just 3. But they each parallel these quote-unquote sub-steps of our state machine for the intake and score curves. And I even have Android Studio code for it, which I will pull up. And so here we are on Android Studio. We have pedropathing, For one thing, here are the constants that you should tune. There's also a tuning section for a whole bunch of things, but typically you don't really touch them. And let's go to an example op mode I have for an autonomous op mode. Few constants I do want to note. Of course, path state path. Path timer. Essentially, we have path timer to say how long we want this robot to stay in a path. And we have a second constant here, which is throughput time. Essentially, what throughput time is how long it takes for the robot to shoot all the balls into the goal. And for us, it is about 1 second. We also have an intake delay timer because our robot, sometimes there is a actual delay between running the actual intake motors. So it needs about 1 second to go on full power. So there is that delay too. And so here's our actual state machine system. So we have in case 0, for example, a preload, and say if our robot, which is just follow, is the thing that Petropathic provides us. We first reset that timer, and then we prepare the outtake. The outtake is just a method I call from a subsystem, which I will discuss in episode 2, or part 2 of the series. And so once we have it to outtake, once it finishes its throughput, we set the path state to 1, which is now the intake. We do the intake. Once it's done, we set the intake off, and then we set path state 2. Then we go to the outtake, or of course the scoring position. And so we let it go to the scoring position. And so we repeat the same thing for intake 3, outtake, intake, and so forth. Right, because a lot of these curves are very different from each other, as the balls are not, positioned in the same way. And so here are our paths. We have preload, intake, outtake. Yeah, of course, you don't have to name it how I did. These are just names, of course. And so this is actually how you would copy paste what you would export from the visualizer into here. And so you can use these paths and just put them here. Follower.follow path start, whatever your path name is. And you put it directly into your state machine. Now, if you want more detail on how to exactly use these methods that Petropathic provides, of course, check the official website. It has a tutorial besides just the installation. It's actually very explanatory, and it's very, very useful. So do go ahead and read that. So that is all I have to discuss for the first part of this introductory video to programming stage. See you all next time.